Okay, so today we are finishing out our learning objectives. The last thing in chapter 3 that we are talking about is trig derivatives. I will give you some ways or tricks or little things that can maybe help you remember them, but part of it is you're just going to have to study them. We are not going to spend much on the whole deriving each one of these. I'm going to show you one that's really easy to see visually as far as justification of why it is the derivative of another function. But we're not going to do that for all of them. So what we are looking at right here, again, because this one's a really easy one to see visually, is what the derivative of the sine graph is. So if we look at this is just your normal sine graph, right? If we talk about finding the derivative of a graph, one of the things that we always looked at was finding maximums and minimums, right? Because a maximum and a minimum is going to have a horizontal tangent with a 0 slope, which will relate to a 0 in our derivative. So if I were to find its maximums and minimums, we've got a maximum up here. Again, a 0 slope means that our derivative would have a 0 at that point. We've got a minimum down here. Its horizontal tangent would be a 0 slope, so it would have a 0 right there. And every maximum or minimum will translate into a 0 of my derivative. Okay? And then looking at the places between that, we've got, thank you. For example, between like this minimum and this maximum, look at the slopes, because that's what we're graphing right now, right? We're graphing the slopes of that. The slopes of the tangent lines of this would be positive, 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 all getting up to a 45-degree angle here, or 1, and all of that would look like this. Positive, 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 till we get to that 0. And then we get to that maximum, and they all turn into negative, 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 till we get to the next 0, which would be below our x-axis to our next 0. And I can follow that pattern all the way through here. And what have I now just graphed? Cosine curve. You are right. And what we're seeing is that the derivative of sine is cosine. Now, does it go the other direction? If I were to do that again, when I get back to my sine curve, and I think I can quickly show you that it actually does not work the other way, directly the same. If I were to use the black curve up here, our cosine curve, and look at its derivative using kind of that same idea, your zeros would be the same. So my maximum gives me the 0 here. My minimum gives me the 0 here. And we start seeing those same zeros that are showing up on our cosine curve. However, if I were to go from like this minimum right here to this maximum right here, those are all positive slopes, aren't they? Positive slopes, meaning my graph would have to be above the x-axis. From here to here, those would all be negative slopes. So from there to there, I would have to be below my x-axis. And actually, what graph are we looking at? Still a sine curve, but reflected. It's reflected. That would be a negative sine curve. So they don't necessarily go directly back and forth, but those two are kind of easy to see side by side. Your green graph, normally your sine curve starts at 0, 0 and goes up back to your midline. The green graph goes down first. That's a reflected sine curve, or a negative sine of x curve. Okay? So that's where they come from. This table right here needs to be copied carefully and memorized. You have to know your trig derivatives. I'll give you some mathematical / non-mathematical hints of maybe something that can help you remember these. But ultimately, you got to find a way to memorize. Derivative of sine is cosine. If cosine is negative sine, the derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent. And the derivative of cotangent is negative cosecant squared. Okay, so here are some things that I have thought about over time, like what can I do to help you remember which ones go with which ones are positive, which ones are negative. So one of the things I'll point out is these two we use a ton, and people tend to be okay with remembering those two. It's the other four we don't use as often. What are some ways we could remember this? Well, everything in trig tends to run through sines and cosines. And if you look at these in terms of sines and cosines, it can help you maybe identify which ones go with which. First of all, notice that tangent and cotangent, the one it is equal to is a singular function squared. So maybe that will help you remember. And which function is it being squared? Well, tangent is sine over cosine. Secant is 1 over cosine. So tangent and its derivative, they both are the ones that have the cosine in the denominator. Compared to cotangent, which is cosine over sine, is equal to 1 over the sine squared. Again, both of those have the sine in the denominator. Maybe that will help. Same thing up here, we've got cosecant, cosecant, cotangent, 1 over sine, and cosine over sine. It's all of the ones that have the sine in the denominator. Where secant is 1 over cosine, tangent is sine over cosine, all of the ones that have the cosine in the denominator. Maybe that will help you remember them as you go. And then the other hard thing to remember is which ones have the negatives, which one don't. And this is very non-mathematical, but maybe a way that could help you is anything that has a co at the beginning of it has a negative in its derivative. Cosine is negative sine. Cosecant is negative cosecant cotangent. Cotangent is negative cosecant squared. The others don't start with the word co and don't have negatives. So that is a very non-mathematical way, but maybe will help you remember which ones of those have negatives and which ones of them don't. But other than that, you're just going to have to find some way, rewrite out this chart, reread over it, make flashcards, whatever it is that's going to help you best remember your trig derivatives. We got to know these. Okay? Any questions? The next slide is actually not anything new. We don't use it a lot, but they will show up every once in a while, most often in the format of finding an equivalent answer in a multiple choice question. Okay, we've done all the work. I've got this answer sitting there. My answer has like a cosine of 2x in it, and I'm not finding that answer in the multiple choice options. Well, what might be happening is it's being written in an equivalent form that we just haven't used in a while, like double angle formulas. Don't talk about those much outside of pre-calc, your Pythagorean identities. Now, the one that's going to show up probably most often is your basic Pythagorean identity, that sine squared plus cosine squared equal to 1. Okay, that one will show up a little bit more often than the rest of them. But again, just some reminders from pre-calc, things that we may want to bring back into our brains as we are heading forward, especially now that we know our trig derivatives and we'll start seeing more questions that involve trig functions. With that being said, and you'll notice it as we go through our examples today, is that you will be expected to remember your unit circle. We talked about some unit circle stuff at the beginning of the year. Again, you need to know whatever method it is that you use to know your unit circle, whether you use the hand trick or special right triangles or memorizing quadrant 1 or just memorizing the unit circle. We have to brush up on that a little bit, or some of these questions are going to be a little bit rough because I would consider all the questions we're doing today to be non-calculator. So although it's tempting to grab our calculators, we should be able to do them without. Okay. Does anyone still need this page? All right. So just jumping into some problems where we're now going to start seeing those trig derivatives show up. Something like find the derivative of y equals x squared sine x. We are looking at a function composed of a product of two functions. X squared is the first function. Sine x would be the second function. And so since it is a product of two functions, to find its derivative, I would use my product rule. Our derivative is going to equal, and the product rule says the first times the derivative of the second. And this is what we are learning today. The derivative of sine, cosine, plus our second function times the derivative of the first. And the derivative of x squared, we use our power rule, 2x. Probably could stop there or clean it up a little bit just to look nicer here. X squared cosine x plus 2x sine x. Eventually, as we use these, I would want to factor, like that has a GCF of x. A lot of times we'll factor that out. So continue to always look for things like that as we're doing these. Any questions on product rule, trig derivative right there? Okay. You try one on your own. Y equals cosine x over 1 minus sine x. What rule are we looking at here? Okay, on this one, we should have done our quotient rule. And the cleanup process was what I wanted to look at most closely on this one. Okay, so product rule says that low D high minus high D low, bottom function times the derivative of the top. So the derivative of cosine would be negative sine minus the top function times the derivative of the bottom. The derivative of the bottom, we can do the derivative of each of those parts. Derivative of 1 is 0 minus, so it'll be a negative derivative of sine. Negative derivative of sine would actually be negative cosine x, right? All over the bottom squared. That's your setup for quotient rule. The cleanup process on this. First of all, I would go ahead and just multiply out the top here, distribute the negative sine x. Sine times sine is sine squared. Negative cosine times negative cosine would be a positive cosine squared. Okay. And this is what I was talking about at the beginning, is sometimes within, we'll see a Pythagorean identity show up right here. There's a Pythagorean identity, cosine squared plus sine squared. That equals 1. Right? So our numerator is negative sine x plus 1, or 1 minus sine x. Okay. Well, if I read at the top as 1 minus sine x, it's easier to see that we can simplify further because there's a 1 minus sine x in the numerator and the denominator, and I can take one of each of those out, leaving me with 1 over 1 minus sine x. Questions on that? Okay. Next one, find the equations for the lines that are tangent and normal to the graph of y equals secant x at x equals pi over 4. This, again, I would consider a non-calculator question. So if I'm writing the equation of a line, remember the things that we need for the equation of a line. We need a point on the line that comes from the function. We need the slope of the line that comes from the derivative. So we start with, it doesn't matter what we start with, let's start with the point. They tell us the x value, pi over 4. The y value comes from plugging that into our function. So if I plug that into our function, I'm looking for the secant of pi over 4. And this is where we have to go back to our unit circle. All right. First of all, it might be helpful to remember secant is the reciprocal of which function? Cosine. And the cosine of pi over 4? Square root of 2 over 2. Okay. So if I do its reciprocal to get secant, turning square root of 2 over 2 upside down gives us square root of 2. 2 square root of 2 over 2, which would be square root of 2. So if we are not remembering our unit circle, might need to add that to our list of things we need to go back and review and or come in and talk to me about. That's our point. We need the slope. Slope is going to come from our derivative. So we need to find our derivative of that line, and this is where we're going to go back to that table that we just made of all of our trig derivatives, right? Something we're going to have to practice, but the derivative of secant, remember? Secant tangent. Okay. Secant tangent, and we specifically want to know what that is when x equals pi over 4. So we're going to look at that at pi over 4. Secant of pi over 4 times tangent of pi over 4. We just talked about secant of pi over 4, right? Still square root of 2. Tangent of pi over 4. You remember what that is? 1. Okay, so our slope, which is our derivative, right? Square root of 2. So then finishing out the question was write the equation of the line tangent and normal. So let's write our tangent line. Y minus square root of 2 equals our slope, which is also square root of 2, times x minus pi over 4. Our normal line, same point, opposite reciprocal slope. Change the sign, turn my slope upside down, which, let's talk about that real quick, probably wouldn't see negative 1 over square root of 2. That would probably get rationalized to negative square root of 2 over 2. All right, usually we don't see it like this. I would be fine if it's a free response. You 100% can always leave it like that because you can equivalent forms. But we would usually see it as probably a square root of 2 over 2 for that slope. Any questions? Okay. All right. Harmonic motion. Harmonic motion is always in a company with trig functions themselves because trig functions model harmonic motion. And harmonic motion is something that we see in the world a lot. Like this one talks about the bobbing weight at the end of a spring. If you were to put a weight on the bottom of a spring and then pull it down, the spring would bob up and down. Harmonic motion is used to model things like the rise and fall of the tide, the rise and fall of the sun, the rise and fall of the temperatures throughout the year. If we were to like track the averages, they rise and fall throughout the year. That's harmonic motion. It is modeled using trig derivatives or trig functions because trig functions also have that rise and fall to them. In this question, it says we've got a weight at the bottom of a spring and that we can find the position of the weight at any moment in time by this position function, s equals 1 minus 4 cosine t. T being time in seconds or time in whatever it is. First thing it asks me to do is find the weight's velocity, speed, and acceleration. Well, again, we've talked about this before, but if it says at time t, that's just your generic derivatives, right? We're going to leave the variable in there if there's a variable in there. We're not doing this at a specific t. We're just doing a generic derivative. At time equals t, at any moment of time, anytime it says that, we're just doing the generic derivative. So let's look at our generic derivative here. So first one's first, the derivative of our position function would be the velocity function. and taking the derivative of our position function, the derivative of 1 is 0. If we've got a constant multiplier, remember the constant multiplier can just continue to sit out front, so it's -4. The derivative of cosine, negative sine t, clean that up. Negative times a negative is a positive 4 sine t. Our acceleration is going to be the derivative of our velocity function. So now I'm going to take the derivative of 4 sine t to get acceleration. Again, the constant multiplier can just sit out front, and we would do the derivative of sine of t, which is just cosine t. The last things last, speed. Speed can come from your velocity function. Remember that speed is the absolute value of our velocity. Well, that would equal then the absolute value of 4 sine t. Do I have to put the absolute value symbols around there? Yeah, think about your sine graph. Does your sine graph ever have negative values? When it dips below our x-axis, it does. So the speed needs to be the absolute value of 4 sine t, because this could be at any point along that graph, which could include negative values. Part B, find the weights of velocity, speed, and acceleration at time equals pi over 4. All we have to do now is go back to those 3 functions we found and evaluate them at pi over 4. So our velocity function at pi over 4 would be 4 sine of pi over 4. Okay. Sine of pi over 4 is our square root of 2 over 2, so 4 times that would simplify down into 2 square root of 2. Your speed is the absolute value of that, but that's already a positive number, so it's not going to change, square root of 2 over 2. Our acceleration, again, just plugging in pi over 4 for cosine of pi over 4. Cosine of pi over 4, we actually already talked about that one a couple slides ago when we were trying to find secant of pi over 4. Cosine of pi over 4 is also square root of 2 over 2, so we get the same answer. 4 times that gives us 2 square root of 2. Okay, the last part, describe the motion of the weight. So again, if you're picturing what's happening, we've got a weight on the bottom of a spring. When we describe the motion of it, we're going to talk about it in time. We got to talk about whether it's heading up or down, forwards or backwards, right? And so we have to consider both its, when we describe the motion of something, its position and its velocity, right? So the position is going to tell us where it is at different moments of time, like where it starts, where it changes directions, things like that. And our velocity is going to tell us which direction it's heading between those moments. So if we look at where it starts, we would look at our position at time equals 0. And our position at time equals 0, 1 minus 4 cosine of 0. What is the cosine of 0? 1 times 4 is negative 4. 1 minus 4 is negative 3. So at the start, our position of our weight is at negative 3. And then we want to know which direction it's heading. Well, which direction it's heading, we need to look at our velocity function. Our velocity function being 4 sine of t. And I want to know, first of all, where it is 0, so I know where it hits its maxes and mins, and then we can look at which direction it's heading between those times. So I would set my velocity equal to 0, and I have to remember how to solve a trig equation. Divide by 4, and I would do my inverse sine of 0, or think about my unit circle. Where on my unit circle is the sine 0? Well, if we think about each of the places where that's going to happen, your sine value is the second number in each of those ordered pairs, right? So if we look at our options 0, 1, 0, and negative 1, sine is 0 here at an angle of 0, or a time of 0, and also at pi. So the two t values that would make sine equal to 0 would be at 0 and at pi. Well, we already looked at time equals 0. Our function is, our weight is down at negative 3. Where is it at pi time? Pi seconds. So at pi seconds, if I look at my position function, 1 minus 4 cosine of pi. Cosine of pi is -1, right? So 4 times -1 is, that would be 4. 1 plus 4 is 5. So there it is. There's our minimum and our maximum, right? Minimums and maximums happens at zeros of our velocity. And I can see where that's happening, and knowing that this harmonic motion reoccurs over and over, we're going to go back and forth between our minimum and maximum every pi seconds, right? Every time we get around to a pi seconds, we're going to hit a minimum or a maximum. So describing the motion of the weight, at the start, our weight was pulled down to -3. They let go. After pi seconds, it hit its maximum at 5, and it will continue to oscillate between its minimum -3 and its maximum of 5 every pi seconds. Questions on that? Okay. The last thing, and we don't hardly ever see this, but I do want to introduce you to the vocab, is the third derivative of our position function. First derivative being velocity, second derivative being acceleration, third derivative is called jerk. So if they ask you to find the jerk at a time t, they're asking you to find the third derivative is all it's asking for. Okay, so this is just a good chance for us to practice taking the derivative of a trig function again. If the question is find the jerk at time t for the following, jerk is the change in acceleration or the third derivative, the derivative of your acceleration function. So we just keep taking our derivative 3 times. So I start with the derivative of 1 plus 2 cosine t. Again, the derivative of 1 is going to be 0. Our constant multiplier will stay that constant multiplier, but the derivative of cosine is negative sine. So the first derivative would be -2 sine t. Yeah. No, just that it was our new word today. Second derivative, again, my constant multiplier sitting out front. Derivative of sine is cosine. So that'd be -2 cosine t. And our third derivative, yes, the -2 sits out front. The derivative of cosine, however, is negative sine t. So that negative becomes a positive. So we go back to +2 sine t. I will tell you right now that the negative positive thing when doing derivatives of sine and cosine is where a lot of people will make their mistakes. So just slow down on that whole, when I take the derivative of this, does this change the sign or keep it the same as you are going through that, especially as we do multiple derivatives. Any questions on that? All right. Your assignment is on page 146, 1 through 10, 13, 17, 21, and 38.